Now that we have these tasks defined for the work, which we did once again by breaking down the process of producing that product into a series of tasks or activities and studied the time of those, we can now go in and start to associate things like ergonomic studies and work instructions on how to perform the task. As I told you before, we're now linked in what parts we're going to be putting on during this task that were essentially parts we're consuming, and tools that we require. It's all hung off the activity. Now the challenge is, where do I perform this activity? And so we go through a technique called line balancing to assign these activities or tasks to workstations along the line. Of course, the amount of tasks we can put in a station are limited by the maximum cycle time that that station can have. Essentially, an assembly line should be paced so that each of the station has just about the same amount of work. That time that's consistent between workstations is called a takt time, or a pace of the line. And that line pace then will determine what the throughput or output of that line, what it can produce, how many units per hour, how many units per day. And of course, if production volumes ramp up on that, then you're going to have to drop those cycle times down for each of the stations, essentially dropping the line's takt time down and allowing you to produce, sometimes then involving more stations, typically involving more stations, and getting that cycle time down, moving those those tasks across to even more stations, and thus each station has fewer tasks. Once we've done that assignment, we'll take a look at that. We now have quite a bit of information. Once again, information that we have because we associated parts and tooling and work instructions and ergo studies and space requirements to the tasks themselves. And the two big pieces of information we have is, of course, the information necessary to create the shop floor work instructions and the information necessary to create the in-plant logistics plan. Now, this is an example of a modern line balancing tool. This particular one is also integrated to those videos and the time standards. We're looking here at the sets of bars representing stations here, BB01, BB02, BB03. The colored bars representing different models that are being produced on the line. And the shaded bar representing what we call the average expected work content. Now, you'll notice that, for example, in station BB01, the shaded bars are all above that red line. That red line is the expected cycle time of the station, or as I said, the takt time or pace of the line. And that really just represents the fact that those colored bars represent not just the time to make a unit, but the worst possible time to make that unit or that model, including all potential optional work that might occur. Because not every model is going to have all of the options on it. But if it did, that's how much time it would take up. So then we're going to apply some probabilities. What is the probability, or what is what we call the take rate? The percentage of a particular model that gets these options. And when we apply those percentage, we get what's called a weighted time, a time that you can see down here in the spreadsheet view below those charts. So the weighted time is a probabilistic time that that particular option is going to take due to the fact that it doesn't occur for all models. And it's that weighted time that's really used to create what we call the expected or mathematical average or mean work content for that station, hence its average cycle time. And that's what's shown by the shaded bar. So in a mixed model line balancing example, we're going to need to be able to look at worst case scenarios, and we're going to want to look at average case scenarios, because it's the average case scenarios that we're actually going to do the line balancing exercise around. At this point, it's a matter of moving tasks forward or backward, and essentially moving them into other stations and evaluating the impact. Of course, this tool allows you to graphically drag and drop those very easily. More importantly, of course, it also contains algorithms that you can employ to help. In other words, here, give me an initial alternative. The software will automatically create the best scenario it can. And from there, the human, the engineer, the process engineer can make changes as they wish to improve the process even further. There are no optimal algorithms to these problems because they're just simply too complex, even for modern computers to solve. But modern computers can usually get you 80, 90, maybe even 95% of the way there. So a few minor tweaks will let you finish the process up nicely. One thing you also notice is on that spreadsheet view here in the bottom right, we're also listing the resources or tooling required and the parts required for those tasks. So we now have a list of all the tools and all the parts needed for that particular workstation just by doing the line balance. Now, for line balancing to work effectively, we really need to define the sequence of events that can occur to produce this product. There are actually Initially, there's a precedence of events, and then there's a set of sequences that comes out of that precedence. Precedence is essentially the order in which the tasks can be performed, not that they are performed. So if I have 3 or 4 tasks that could be performed in any order, those tasks will be shown in the diagram in parallel. In fact, you see a couple of parallel streams right here in the yellow bubbles on the bottom of this slide. Those tasks are essentially in parallel. Tasks that have arrows connecting to the right and left are serial. That means that one has to be done before the other. Now, when I have a lot of parallelism, I can create many different possible sequences of events. At the end of the day, unless the line itself has parallel routes, which most don't, this product is going to be produced in a particular order, a set of tasks performed in a particular order, and that is called the sequence. Now, of course, we could just start by default and taking a list of tasks as they were performed today, putting them in a big list, creating a default sequence, and doing our line balancing. And unfortunately, that's how a lot of people do line balancing today in Excel, because even that's difficult to do. But you lose out on a lot of potential opportunities for process improvement if you don't consider the parallelism that might be there, which means that I might be able to do this task ahead of that other task, and by so doing, I might just be able to get this task in the prior station and do a better job of increasing utilization of the station. We're typically finding that by looking at precedents and allowing the system, the software, as well as the engineer to improve the assembly's line balance using all the parallelism knowledge that they have, we can get another 5%, sometimes 10% of productivity out of that line. In other words, 5 to 10% more output with the same people. In today's competitive environments, that's pretty significant. This also shows an example of a type of precedence definition called clustered precedence. As I mentioned, precedence can be difficult. There's no doubt about it that it's a piece of information that's very valuable to the organization, because it says this is the order that this product can be made in. But it's a piece of information that is sometimes difficult to document because there really are so many tasks and there's so many ways they may be able to be performed. So we've invented a technique referred to as clustered precedence, which allows people to define precedence in zones or clusters of the process, and then define the precedence between those zones and clusters. This is much more efficient to author and manage than just sitting down and trying to define the precedence for 1,000 tasks all at one time. But if you could sit down and define the precedence, 10 people could sit down and define the precedence for, let's say, 100 tasks, that wouldn't take that much time. And then it's just a matter of defining the precedence between those 10 clusters of tasks. So clustered precedence is a great invention that really allows the definition of precedence and subsequently sequence to be done efficiently and effectively. The other thing I want to say about line balancing is it isn't just about task assignment. We've talked a lot about that, but it is about defining then or charting and reporting the tooling that's required in the station, the parts that are required in the station, the space that those parts and tools take up in the station, as well as any ergonomic issues that may result by combining those tasks together. For example, most of the ergonomists would agree that you can't have a set of tasks in a station that are performed above a person's shoulders for more than 50% of that person's work cycle. In other words, I can't have a person working above their shoulders for their entire work cycle. That's not ergonomically effective. Other constraints that people often discuss are maybe no more than 5 or 7 presses or twists or connects per minute. Beyond that, we could be subject to a carpal tunnel or a cumulative trauma, repetitive motion type disorder. So we want to identify whether the tasks do involve work overhead, whether they do involve maybe heavy lifting of parts, maybe they do involve presses and twists and connects, so that we can add those up and identify the potential ergonomic risk and hazard by those tasks being in the station. Another thing that the lean practitioners like to focus on is the value-added, non-value-added, and also non-value-added but necessary work that may be performed in the station. It's how much of that station is value-added work. It's really moving that product towards something the customer wants to buy versus non-value-added work, things like walking or restacking the boxes or possibly taping something off that really is just an inspection capability. So we really want to make sure that we're identifying how much work is being performed in a station that's value-oriented so that we know which stations we can perform our Kaizen events on and try to improve even further. But being able to capture this information within the line balancing system and report and aggregate this effectively is a great advantage. And the final thing I'll say about the reporting here is the ability to do what we call current and future state analysis. It's great to be able to know that in a new line balance, here are the tools and the tasks and the parts that I'm going to do in a station. But it's even more valuable to know how does that compare to the tools, tasks, and parts that I had in the station. In other words, what is it that I need to change or move in order to make this new station happen? And so the ability to do these comparisons of current and future state and generate a differential report so that materials handling can make their appropriate changes so that industrial facilities can move the tooling as required are tremendous aids in speeding up the time it takes to go from having a line balance to actually making product. And also, since it's computer generated, removing the human error that often goes with forgetting, oh yeah, I forgot I moved that part, or yeah, I need to move that tool, and then having to expedite or do that at the last minute when you're trying to produce quality